Okay, everybody, here is lecture videos for Chapter 4. I think I actually now have the ability to record videos longer than 15 minutes. However, right now I don't have the time, so I think I'm going to just still kind of go till I get to a convenient stopping point. I'm hoping to make it through the first example on the third page of the notes, and I think that's a decent stopping point for us. You're going to encounter some new definitions, some terminology, and unfortunately some ugly looking formulas. But I'll tell you this, if we take the time and we get some practice with them, once you get your hands on some actual examples, they really aren't as bad or as scary as they may seem at first. So just stick with it, hang with it. Again, watch this video as many times as you need, and I think what's really going to help connect the dots is when you do the homework or when we do some extra questions, in our virtual class. Kind of like with anything new you learn, you got to sort of grind through the nuts and bolts of it first. So anyways, let's do a little bit of this. We're in 4.1, and we're talking about something new, and it sounds intimidating. It's a discrete random variable. It's a new term, but it's really kind of what we've already been doing. So let's just figure out what the hell is a random variable. Okay, a random variable is a variable whose quantitative value is determined by a random event. Okay, all right, a couple things there. Quantitative value. So random variables are numerical. Remember, variables, those are just things we want to study. It could be eye color, it could be heart rate, things like that. Remember, they can come in categorical or quantitative, aka numerical. Random variables are quantitative, they're numerical. Okay, and there are things we're just interested in studying. So their random variables are numerical. They are things we want to study. Like I said, maybe it's the heart rate of a population of males or something like that. Maybe it's the height or weight of a population of children or something like that. Something we want to study, some numerical value we want to analyze. Okay. We usually begin by defining what the variable is, and because we don't want to write it over and over and over again, I don't want to write the height of 13-year-old males. Like, I want to just be able to assign it to a variable. So we'll usually use a capital letter to do that, and then we usually let a lowercase letter denote the actual realized value. So if we're talking about a specific data point, we would indicate that with a lowercase letter. You're going to see all this coming up. Now, there are two types of random variables we're going to investigate. The first is discrete, and then later we will get into continuous. Okay, these are just two mathematical terms that describe numbers. Discrete numbers are numbers that are countable. Okay, in other words, you can make a list of them. They might be finite or infinite, but you can count them. Okay, so here they give some examples of some discrete random variables. All the positive integers, 1, 2, 3, 4, 5, 6, 7, and so on, those are discrete. The number of steps a person takes when they're running a mile, you can count that. It might be big, it might be hard to count, but you physically can count how many steps does someone take when they run a mile. If you look at a backpack and you want to look at the number of books that are in a backpack, you can count that number. Okay, so those are all known as discrete values or discrete numbers. And these could all be discrete random variables. Maybe I want to analyze the number of steps someone takes, and so I'll look at a whole bunch of people running a mile. I could find the average number of steps it takes someone to run a mile and so forth, standard deviation and variance. So maybe that's the thing that I'm trying to study or learn about. Okay, I could have continuous random variables, and again, we're going to talk about it now, and then we're not going to talk about it again until I think chapter 6, I think. Continuous numbers are not countable. There's infinitely many, and they are infinitely close together. You cannot list them all out. So for example, all the numbers between 0 and 1. There's technically infinitely many numbers in between 0 and 1, and it's impossible to list them. I mean, you could just go, well, there's 0.1, and there's 0.01, and 0.001, and 0.0001, and you could just do that forever. So the amount of time it takes a person to complete a mile. Now this is interesting because people have timed miles. You'd say I ran a mile in so many minutes. But technically time is continuous because, yeah, we might say, okay, you ran a mile in 10 minutes and 3 seconds or whatever. But it's not like it ends at exactly 10 minutes and 3 seconds. It's maybe 10 minutes and 3.1112567 seconds. Okay, so in other words, we would consider that a continuous number because you actually can't really measure exact time. You can kind of get an approximation for it. Same with weight. You know, the weight of this backpack holding books, would put it on a scale, and the scale just rounds it to like the nearest decimal or two, right? But really that backpack might weigh 15.1313145.7, and just keeps going, pounds. You know, like at some point we just have to cut it off and say, okay, it's 15.3 pounds. Okay, but technically time and weight are continuous variables or continuous values because you really can't pin down the exact number. You have to at some point round it. Now here's a big scary word, a probability mass distribution function. Damn. What that means is basically if we were to draw a graph of all the possible outcomes that can occur and list how many times they occur, basically a histogram is what I'm talking about. They call it a probability mass distribution function. Oh boy. So maybe I'm thinking about this number of steps to run a mile. Like this could be 1,000, I don't know, 1,000 steps, and maybe you have this many people doing it. And maybe this is, 1,200 steps, and you have fewer people doing it. Maybe over here is, 900 steps, and you've got not many people doing that. Okay, so I mean, you can kind of get an idea on what the general shape of this curve might look like given on how many steps someone takes. Right? You just count how many people landed in this category, and that's how tall you draw that dot, just like a histogram. Now, a probability density function is the same idea, but when you're talking about continuous numbers, there's infinitely many. So in other words, I'm trying to cram infinitely many dots here, right next to one another. There's infinitely many dots. And what happens when you end up doing that is you end up just getting a smooth connected curve. There's no space in between the dots because there's infinitely many numbers in between each dot. Okay. So again, for now, we are just going to focus on discrete. Okay, so that's all you need to worry about now. These are things you can count. Things that are countable. A probability distribution. We have talked about probability distributions before, right? We've looked at frequency distributions. That's how many times something occurs. You list out how many outcomes there are and then how many times each outcome happens. In the chapter 3, we defined a probability distribution. Didn't we say you list out every outcome that can occur and you tie to it, or also list the probability that each one of each outcome happening? Same thing here. So a probability distribution of a random variable, the same idea. What you do is you first list all possible values the random variable can take on. All possible outcomes that random variable gives, and then along with that you list the probability of each outcome occurring. Okay. So a distribution we're pretty familiar with. All the outcomes, and then if it's a probability distribution, you're going to list the probability of each outcome. If it's a frequency distribution, you're going to list all the outcomes and you're going to write the frequency, how many times each outcome occurred. That's like our histograms back in chapter 1. So here's an example. They say that suppose the probability distribution function, shortcutted to PDF, we'll see that a lot, for the number of years it takes to earn a bachelor's degree is given in the table below. So this is my random variable, and it represents the number of years that it takes to earn a bachelor's degree, a Bachelor of Science, okay? So what they've done is they've listed two things. They've listed all possible values that the random variable takes on, according to the study they did, and then they tie to it the probability of each outcome occurring. Okay, that's what we're looking at here. So they say in words, define the random variable x. What does that mean in words? And whenever you're going to write out a probability distribution function, this should be the first thing we do. Tell the reader what x is. X is the number of years it takes to earn a Bachelor of Science degree, according again to this data that they've collected. Okay. All right. So that is my random variable there. Part B says, what does it mean that the values of 0, 1, and 2 were not included for x, the random variable, in this probability distribution function? Boy. So in this probability distribution, they're saying, how come x didn't take on the values 0, 1, or 2? It starts at 3. Well, what that's indicating is that from the data they looked at, nobody got a Bachelor's of Science degree in 0, 1, or 2 years. Okay. According to their data, no one got a bachelor's degree in 0, 1, or 2 years. I mean, that doesn't mean it's impossible. It can happen. It's just not according to what they researched, right? The probability was 0, so they didn't even bother listing it. If the probability of your event is 0, they just leave it off of the distribution here. So let's take a look at this one. It says, what is the probability of a random student taking more than 4 years to earn a bachelor's degree? The way we would write that notationally, because again, that's wordy. We don't want to word all that stuff out. So symbolically, we would just say, okay, well, what's the probability that x is greater than 4? That's the probability that x, which is the number of years it takes to earn a bachelor's degree, is more than 4. Okay. Well, if we're talking about, what's the chances that it's more than 4, that means we're looking at it could take 5 years, 6 years, or 7 years. What's the probability that it takes 5, 6, or 7 years? Think about the probability rules we just learned. I'm saying 5 or 6 or 7. We know with an or statement we add probabilities. So this would be 30% plus 15% plus 10%. I'm adding up those probabilities right there. If my math is right, that should be a total of 0.55, or there's a 55% chance that it will take someone more than 4 years. Let's just write that out. More than 4 years to get a bachelor's. That was me. I was in that group. I think I did it in 5 or 5.5, somewhere around there. Okay, let's see. Next page. This kind of looks familiar. We've done this before, where we've talked about probability distributions in chapter 3. We said that a couple things have to happen. So in order to have a valid probability distribution of a random variable, these two things must happen. The sum of all the probabilities must be 1. Again, if you're listing out every possible outcome that can happen, along with the probability that it happens, there's a 100% chance one of those things will happen. So the probability should all sum up to 1. And the probability, or sorry, each individual probability has to be between 0 or 1, and it can include 0 or 1. That's what it means, inclusive. It might include 0 or 1. So in other words, we're not talking about having anything, nothing's going to be a 400% probability of happening. That doesn't make sense. It's always between 0 and 100%, though it might be 0 or 100%. I just scrolled up and you saw this. Don't panic, don't panic. Let's take a look at this example. And we did something similar to this again in chapter 3. It says, why aren't the following situations examples of probability distributions of a random variable? So in other words, what's wrong with the picture here? So what they've done is they first defined what the random variable is. They said let x be the outcome of a coin flip, either heads or tails. So they've listed the two outcomes. They've listed the probability of each outcome. I mean, those add to 1, right? So we got that done. And they are in between 0 and 1, or including 0 and 1, so that's down. So what's the problem here? The problem is if you go back to the last page, remember a random variable has to be a numeric quantity, right? Something that's quantitative. This is qualitative, heads or tails. That's not something that's numerical, right? So it turns out that we can still study this. You just have to rephrase the random variable, okay? We shouldn't say that x is the outcome of the coin flip. We should say x is the number of times I get heads. Because now it's countable, right? Now if I flip a coin 100 times or whatever, I can count the number of times I get heads. So you got to be careful with the wording. The way it was first worded, it's not technically a random variable because that is not a quantitative value, it's qualitative. So you got to make sure they're worded so that you're talking about quantitative things. Now here on this example, part B, it says senior executives were asked when job applicants should discuss salary. The table below is created from their responses. So they've got the number of interviews. So they, these senior execs says you should either talk about salaries on your first interview, second, or third, and that's the probability or the relative frequency basically that said, yeah, do it on your first one, or on your second one, or on your third one. The problem here, I can just kind of quickly eyeball, is that if you add these things up, this ends in a 6. Okay. So it's not going to end in 1. If you add all these things up, what is that? That's 56. They add to 0.76. They do not add to 1. So this isn't a complete list, really. Again, those probabilities should be adding up to 1. So this is why these are, they aren't, or they are not correct probability distribution functions. Okay. This is where it's going to get painful visually, but again, once we put together an example, and I'm going to do one example on the next page, and I think that's where I'm going to end it, I hope you'll see that it is not as bad as it looks. So, when we learned in chapter 2, I believe, about how to find mean and standard deviation. And remember, if you have your standard deviation, you have your variance too, because it's embedded in the formula. That's all we're going to talk about now. How do you find the mean and standard deviation, or variance, of a discrete random variable? So in other words, maybe my random variable could be the number of sprinkles on a donut. It's countable, it's numerical, maybe that's it. Maybe I want to know the mean. I want to know what's the average number of sprinkles on a donut. Maybe I want to know the standard deviation, so on average, how far from the mean do we expect to see the number of sprinkles on a given donut? Okay, so let's break down this formula and not get too intimidated by it. Again, we're talking about the mean of a discrete random variable, And this is how we calculate it. First of all, we do use the symbol mu. Well, for mean, we're referring to mu. I actually use this a lot. There should be parentheses there, e of x. This is called the expected value. So mean or average is the same as expected value. Those are all three words that can be used to describe the average. Okay, but for, I don't know, I just use the word expected value when talking about these things. So the expected value of this event, the expected average number of sprinkles on a donut. Here's what we do. It's the sum. Remember, this means to sum things up, that you're going to add up all the data values you have. And so I'm going to add every data value times the probability of it happening. Okay, so it's really not too bad. You're going to take your data value times its probability, which you get right out of a distribution function, data value times probability, and then you're going to add data value times probability and data value times probability. Again, not for one of these because this is not a legitimate random distribution, but that's how you would calculate them. And what it means is in the long run, over many, many trials, many donuts, that's the average number of sprinkles you would expect to find. That's the expected value of sprinkles you would expect to find on your donuts. Okay, again, this looks hideous. Once we actually do an example, it's not going to be that bad. And it doesn't get any better yet. They're going to talk about variance and standard deviation. If you recall, remember, the variance is equal to your standard deviation squared, right? We learned that back in chapter 2 that if you have your standard deviation, you could square it to get your variance. Okay. And when it comes to analyzing things, I think the two things we really want to be familiar with are expected value and standard deviation. I would say those are the two primary things we use to analyze a random variable. Well, here they tell me how to get my variance. Okay, you could write it this way, the standard deviation squared, or you could just call it the variance of this random variable x. Okay, what it is they take your data value minus the expected value of that random variable. So that right there is telling you how far away each data value is from the mean. Doesn't that sound familiar? That's exactly what we did with standard deviation. How far each data value is from the mean. How far each data value is from the mean. Remember, some of those will be on either side of the mean, so you'll get some positive, some negative answers. That's why we square it to get rid of that negative, just like we did with standard deviation. And in this case, we then multiply by the probability of each data value occurring. Okay. Again, once we get our hands on it and do one, it's not going to be that bad. And then if you take this equation and solve it for sigma, you would have to square root both sides. We see that sigma equals the standard, which is the standard deviation of x. It equals the square root of your variance. Remember, when we did standard deviation by hand, wasn't the very last step to square root everything so that we're undoing that square? Same idea. The interpretation is that in the long run, over many trials, on average we will get a value of about sigma units away from the mean. So we might find that after sampling a ton of donuts, we sampled 1,000 donuts, and we might say on average there's, I don't know, 40 sprinkles on the donut. That would be the expected value, the average number of sprinkles. If the standard deviation is 5, that means that, okay, yeah, on average every donut has 40 sprinkles, but we also expect to see it fluctuate plus or minus 5 from the average. You know, anywhere between 35 and 45 is what we expect. It's the standard deviation or the standard distance from the mean. Okay, let's try one of these on the next page, and then I'm going to pause this video and head on to something else, and I'll be back for more. So here they give a random variable. They say find the expected value, variance, and standard deviation for the random variable. We're going to do this one by hand. We're not going to do all these by hand, just in the very beginning we will, and then we're going to start relying heavily on StatCrunch soon. One thing they didn't do is they didn't tell me what the heck this random variable represents. I think they should include that. So let's just say the outcomes are 10, 12, and 30, or 20 and 30. So maybe these are like the number of tickets you could win at an arcade game or carnival game. So let's say x equals the number of tickets won at, let's say, an arcade game. Okay. So when you play the game, you could win 10 tickets. There's a 30% chance that's going to happen. You could win 20 tickets. There's a 50% chance that's going to happen. Or you could win 30 tickets. There's a 20% chance that's going to happen. For this particular game, those are the only outcomes possible. I know they're the only outcomes possible because in a probability distribution function, you have to list every possible outcome. Okay, so find the expected value. Remember, that's the mean, but I like the word expected value. So expected value of x. The way you find the expected value of x, again, is you take each data value, each outcome, times the probability of it occurring. So I could win 10 tickets 30% of the time. Or, plus, I could win 20 tickets 50% of the time. Or, plus, I could win 30 tickets 20% of the time. That is my expected value. When I crank that out, I think I should get 19, according to what I wrote down earlier. So what the heck does that mean? I can't win 19 tickets, right? I can only win 10, 20, or 30. But if we were to interpret that, that means that over the long run, every time we play the game, we expect to average a win of 19 tickets. I mean, I'm going to win either 10, 20, or 30, but over the long run, it averages out to 19 tickets per game. We average a win of 19 tickets per game. Again, don't get confused thinking that, like, well, I can't win 19. You're right. We can only win 10, 20, or 30. But sometimes you win 10, sometimes you win 30, sometimes you win 20. So again, it averages out to every time you put a quarter in the machine, you're going to average over the long run 19 tickets per quarter you play. Okay, let's do the variance. The variance of random variable x. If you look back on the page, what we were supposed to, on the previous page, we're supposed to find out how far is every data value from the expected value. So I want to take 10 minus 19. That's how far the data value is from the expected value. I'm supposed to square that so we don't have to worry about some being positive and some being negative. And then I'm supposed to multiply by the probability of getting that particular data value. So that's for 1. And then I need to add and do the same thing for my next option. How far is 20 from what we expect? Square it and multiply the probability of getting a 20. That gave me that. Plus, for this guy, how far is 30 from what we expect? Square it so I don't have to mess with any negatives, if there are any, times the probability of getting a 30. Now you better double check, but I have written down that this all comes out to 49. I don't know if I actually did it or made it up, but double check that that gets 49. Now for the standard deviation of x, which you could write this way or call it sigma, remember the standard deviation is just the square root of this number. Remember, all we do is take the variance and undo all this squaring we did. So it would be the square root of 49. It'd be 7 as my standard deviation. And what that means is that over the long run, many, many times you play the game, I know I can expect to win 19 tickets per game. But we also understand that there's some fluctuation there. This is the fluctuation, right? Every time you play the game, we can expect to be about 7 units or within 7 units from 19. So over the long run, we can expect the number of tickets won to be about 7 units from 19. To be on average, let's say, because it's the average distance, on average 7 tickets from the expected 19. Okay? All right. I'm going to stop it there. Yep, and I'll get back to you with more later. Okay, see you soon.